Our last topic is fission and fusion. There can be non-radioactive nuclear changes. So some nuclei are so unstable that if their nucleus is hit just right by a neutron, the large nucleus will split into two smaller nuclei. That's called fission. Or small nuclei can be accelerated to such a degree that they overcome repulsion, smash into each other to make a larger nucleus. That's called fusion. Both fission and fusion release giant amounts of energy. Fusion releases more energy than fission. So here's an example. We have uranium being hit by a neutron, and it breaks into two smaller nuclei, barium and krypton, and then a few other neutrons, and then a whole bunch of energy. So you can see that since it's releasing other neutrons, this can be a chain reaction. Here's the chain reaction. So we've split our uranium with a neutron, but then we send off 3 more neutrons, and we get exponential growth of the reaction. So this was used to make atomic bombs. So here's a letter from Albert Einstein in 1939, so towards the beginning of, well, just before the First World War, actually. Some recent work by Fermi and Celsard, which has been communicated to me in a manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action by the part of the administration. So then some facts and recommendations from him. So fissionable isotopes include uranium-235, plutonium-239, and plutonium-240. It's important to know that natural uranium is less than 1% uranium-235. So if you just got some uranium from a mine, it's not going to undergo this chain reaction. It's not enriched enough in uranium-235. It's mostly uranium-238. In order to create this fissionable uranium, you need to enrich it in uranium-235. If you want weapons grade, it has to be to about 7%. Reactor grade for a nuclear power plant is about 3%. Comparing nuclear power plants to coal burning, nuclear power plants will use about 50 kilograms of fuel, so enriched uranium, to generate electricity from 1 million people, and then there's no air pollution involved. Coal burning uses about 2 million kilograms of fuel to generate enough electricity and produces all sorts of pollution. Now, nuclear power is not without its costs. If the core melts down, say like in Chernobyl, it's a big problem. So the water from the core, it loses water, and then the heat from the reaction melts the core, and you end up with a problem. Also, the waste, while there's not as much of it, is highly radioactive. Currently, we just kind of shove it underground. Transporting it is a problem. And then there are some nuclear power plants that are no longer safe to operate. How do we deal with that? So while we get less pollution, there are significant costs to running a nuclear power plant. All right, let's go back to fission. Where does the energy come from? What happens is Einstein has this E equals mc squared, very famous equation. So energy is mass times the speed of light squared. Some of the mass in the nucleus is converted into energy. And so each mole of uranium-235 that fissions produces about 1.7 times 10 to the 13th joules of energy. Now, if you have a very exothermic reaction, you're only going to get to about 10 to the 6th joules per mole. So it's orders of magnitude higher than a chemical reaction. So when a nucleus forms, some of the mass that separate nucleons is converted into energy. And so that difference in mass between the separate nucleons and the combined nucleus is called the mass deficit. And then the energy that's released when the nucleus forms is called binding energy. And so the greater the binding energy per nucleon, the more stable the nucleus. So here's a picture for you. We have the most stable nuclides here in the middle. The ones on the left of it undergo fusion. The ones on the right will undergo fission. So fusion will combine light nuclei to make a heavier, more stable nuclide. This happens in the sun. The energy in the sun is from fusion of hydrogen isotopes to make helium. It requires a high input of energy to initiate the process because you're combining two positive charges together, and that costs a lot. But then it produces 10 times the energy per gram as fission, and there's no radioactive byproducts. So it would have some benefits, a lot more energy, and then you don't have any radioactivity afterwards. But currently the only working application is the hydrogen bomb. So the way harnessing that energy is not something that we can currently do. We can only destroy things with the energy. How do we make new elements? So if you notice, the bottom row of your periodic table has a lot of artificial elements. Let's talk about how those are made. Basically, you can smash high energy particles into a target nuclei and produce a new one. So those particles could be radiation or charged particles. An example here is Rutherford made oxygen-17 by bombarding nitrogen with alpha rays from radium. But the more common way of doing this is to make those artificial elements. So californium CF244 is made by hitting uranium-238 with carbon-12 and a particle accelerator. This here should be californium, not oxygen. So particle accelerators are how we make those heavy artificial elements. So let's practice figuring out how to make, or working with these nuclear equations again. Predict the other daughter nuclide and write a nuclear equation for each of the following. So bombarding nickel-60 with a proton to make cobalt-57. So we have nickel-60, and nickel is element number 28. We are hitting it with a proton, which has a mass of 1 and a charge of 1, to make cobalt-57. So we're making 57 cobalt, and then cobalt is element number 27. So we're going to end up with, in addition to our cobalt-27, on this side we have 61, and this side we have 57, so we're going to end up with 4 there. On this side we have 29, 27, so 2, and that is an alpha particle. All right, what if we bombard nitrogen-14, so N14-7, with a neutron. So a neutron has a mass of 1, a charge of 0, and we get carbon-12, carbon's element number 6, plus then we have to figure out what else there is. So for mass, We're at 15 on this side, 12 on this side, so that gets us 3. For charge, we're at 7 on this side, 6 on this side, so that's 1. And that is hydrogen 3, or tritium. All right, what about bombarding? Californium, 250. And then californium is element number 98. With boron 11, boron's element number 5, producing 4 neutrons. So neutrons are 1, 0, n plus, so on this side we have a mass of 4, on this side we have a mass of 261, so 261 minus 4 gets me a mass number on this side of 257, and then 98 plus 5 gets me a atomic number of 103, and element number 103 is lawrencium, Lr. So that's how you would work out those equations. All right, let's talk about some of the other uses for radiation. Radiation is high energy. It can knock electrons out from molecules, break bonds. If you do that to cells, it can cause a lot of damage, cause malfunction in the cell. So sources of radiation for people in the US, there's natural radiation. So you just get some from being around. An airplane ride gets you a little bit higher. Medical procedures, x-rays will get you, some radiation. They need radiation to produce the x-rays. And then you can get some radiation from consumer products, lots of sources of radiation. So some radiation exposure is expected, isn't going to hurt you overall. There are medical uses of radioisotopes, and so certain organs will absorb particular elements, and so you can use tagged isotopes and basically a Geiger counter to trace, how a certain organ is functioning. And you would want to use a radioisotope that's low ionizing, so it gives off beta or gamma rays. Alpha is going to cause some damage. So an example of that is the thyroid will absorb iodine. There we go. Iodine 131. You want something with a pretty short half-life, and then you can check different organs or systems. Here's some bone scans using radiation. PET scan is positron emission tomography. We use fluorine-18 tagged glucose, and that will let you see how your brain is working, because your brain uses glucose as its primary energy source. Non-medical uses include smoke detectors, insect control, food preservation. That's what this picture is. If you irradiate strawberries, for example, you can kill off that mold that grows on them and keep them good for longer. And then radioactive tracers are very useful in chemistry. You can follow a tagged atom in a reaction, figure out where it goes. Useful for determining metabolism reactions in cells. And then chemical analysis can also use radioactive isotopes.